Let's start up here. First off, the elephant in the room here. I'm dressed up. We have to, the district decided that for our enrollment is down. And so they made an edict that we have to follow now, that teachers have to be in a suit and tie. And women have to dress up a certain way, have to have her hair a certain way, to try and increase enrollment for the school system. Okay. Now that was a bad April Fool's joke, but I do it, I'll take this stupid thing off. I do it in honor of the exactly 1 year ago today was our first Zoom. I remember it because it was April 1st. And so I did this, the suit thing, the old suit joke with the students. So it was 1 year ago that you started Zooming with your teachers. All right. So I used to well, I'll tell you this story. So back in the day, back before we'd had much internet, kids didn't really have phones. So I used to always do this April Fool's joke on them. I would set it up a week ahead of time, and I'd talk about how the planets, were going to line up, Jupiter, Saturn, and they're all going to be lining up here. No one ever checked me on it because they didn't really have a way to do it that quick, and then forget about it at night. So I'd say that week, I'd say, okay, Thursday, the planets are all going to line up. So then Thursday, say it was Thursday, was April Fool's Day. Then Thursday, I would say, okay, so today, looking at the time where the Earth is, where the planets are like right above us, and they're all lined up, all 9 of them or 8 of them. I guess 7 of them are all lined up. And so the big ones are out there. So we could, if you jump up, the theory was if you jump up in the air, because of the combined gravity of these other planets, you'll stay up in the air a little longer and you'll notice it. And so we would all jump up in the air at once and then come back down, then we do it again. And then there was always a couple of students that would say, yeah, I did notice that. That was a good one. Those were the days when you could fool students easily. Now, if I do it, kids just look it up on the phone. What? There was no planet alignment. Can't have fun no more. All right. So here we go. Open all that up. This is class number 24, coming down to the end of Pkt5. We're a little behind on Pkt5. Hopefully we'll get through at least maybe the first part of 511. We'll finish 5. Well, no, we're going to work on 5.9 today. We're not going to finish it. We'll finish 5.9 tomorrow. We'll maybe get a chunk of 5.10 done. Wrap up 5.10 on Monday. Start 5.11 on Monday. Do 5.11 Tuesday, and then wherever we're at, we'll just stop there for next week. And then we'll just pick up 5.11 is the most important sheet of the year. So we'll pick it up again on packet 6. Let's see. Yesterday, if you all were here, I told them all them about the we went over each little problem and just kind of gave you a heads up. But on the take-home test, every one of those problems is on the Facebook group, so you can go in there and look at each problem and then check to see if you're doing it right. All right, and you can also, well, the answer isn't there yet, but you can say, and I think I'll start putting some answers. I'll actually add the answers if I remember to do this as I'm working them. I'll add my answer into the comments, and then we'll see, if you agree. I might be wrong. That's where we're at. The dino hunt. That's due. The thing is due Tuesday night. Now, this meet table 4. What we're going to do here is I'm going to stop the recording, and then I'm going to meet one of you, whoever is the brave soul. Now, you have, then we all get to meet you. I interview you, I ask you a few questions, and this is what I do in class on Tuesday or Thursday. But the only stipulation is you have to turn your camera on, but don't turn it on until I pause this. Okay, I'm gonna pause the recording now. Recording. Hold on a second. Hey, there's these fiber optics guys in my yard. They're ringing my doorbell. Let's pause recording for a second. All right, so I did that. Have to meet Bennett. So on Tuesday, I showed you video of it, but they went out in the hall and we did the duck walk lab. We were relying on this part of Hooke's law. We were stretching the spring, and as more we stretched, the more force we got. And so we used that to come up with 2 newtons, 4 newtons, 6 newtons, 8 newtons, and 10 newtons of stretch force on this cart. And that made the cart accelerate. And so I want to use this as sample data. So even though we didn't go out there and do it, you saw it happen. But this is what they had to do in class. They have to now take these numbers here, and these are the times these are sample, look at the morning data. These are pretty close to sample times that they were getting. And so on this table on the front of 5.9, we kind of have to do this. Otherwise, I'm just waving my arms the whole hour. So we need to actually have some data to mess with. So let's go through and fill out the table. We're not going to worry about this last column. Just mark it out. It's not worth it. Mark out that last column. So we'll fill out, and then we'll mark out the raw times. We're just going with the average time for each run. Okay, so if you remember the pictures, so they move that cart, and these are the times. And so the average velocity, we'll go through one line with you and then let you do the rest. The average velocity is just the total delta x. We're going to use this equation. Total delta x over tau, so 3 over tau. So tau being the total time. And so like in this case, if it was 2.4 was the average time, then we would have 3 divided by 2.4. So our average time would be, our average velocity would be 1.25. We'll go 2 digits, 1.3 meters per second. Then our final velocity, we're going to use the equation. It's a pre-orange equation. So we'll use this pre-orange equation here. Hold on. Okay, hold on. Write that out. Okay. Now the pre-orange equation looks like this. Blow it up here for you. The pre-orange equation is V bar equals V naught plus V final over 2, but our V naught was 0. So that part goes, green kill pin, kill that. That goes away. And so our V bar, our average velocity is simply V final over 2. So V final is twice V bar. So whatever you got for this column, this average velocity column, you just double it and you got the final velocity. So in this case, for this one will be 2.6. 2.6 meters per second. And then it says, what's the change in momentum? So the change in momentum, the mass we were using was 6.3 kilograms. So the change in momentum is simply mass times V final minus mass times V naught. V naught was 0. So all we do now is multiply this column by 6.3, since that was our mass. So 6.3 times 2.6 will give us 16.4. And I'm just going to go to 2 digits, so 16. And these are all kilogram meter per second. You don't need to put the units every time because the units are at the top of the column, so it's not really necessary. All right, so now you do the same thing I just did for the 2.1 seconds, 4.5, and the 1.5. And I'll do it silently. Do a little class data here. Yeah. I'm going to push pause. And if you're at home watching this, go ahead and do it. Then you can, we'll come back, we'll finish. So there's our data. That'll be for our virtual data. Okay. Doesn't look like much. Can't see a pattern. If one thing, it's not in order, so that doesn't help. But what we're going to do here is using these numbers, we're going to concentrate on these columns, the force column, the average time column, and the change in momentum column. We're going to compare these numbers, put them into different, there's, you know, you look at them at a magic triangle, well, how can I possibly rearrange these variables to put them into an equation? And so if we do that, let's take, for instance, the 4 newtons. In fact, we're not going to look at the 4, 6, and 8 normally are the 3 best runs in duck walking. So let's try the 4 first. And so for 4 newtons, you say, well, is this, that's the force, is that equal to T times delta P? So we just take pure numbers. Looking at our pure numbers, 3.2 times 12. Okay, I get 3.2 here. Okay, I'm in the 4 Newton section. 3.2 seconds here, 12 kilogram meter per second there. Multiplying to get 38.4. Well, 4 is not obviously not 38.4. That's not even close. Well, now let's take it as T divided by delta P, which is 3.2 divided by 12, and I get 0.27. Now let's take 12 divided by 3.2. 12 divided by 3.2 gives me 3.75. So you go, well, which one's closest? Obviously 3.75. So this is the correct one there. And now you do the same thing I just did, but now do it for 6 newtons and then do it for 8 newtons. And I'll do it too. I'll do it in silence, and you do it on your paper. You're verifying here. 38 again. And, 0.15. 6.7. So that still looks good. And then finally, one more just to make sure that this data seems to be working out. Now we're doing this and this, right? Yeah. Times 35, 36. And pretty obvious now which one's correct. 0.12. 8.1. So it looks like by far, this is like I say, it's sample data from, but it is live data from the morning classes. And so it looks like then our formula is force equals the change in momentum over time. One way of determining a new relationship is to do an experiment and then measure things and then see which one correlates the best, which is my best possible correlator. And this is it. And as a matter of fact, this is Newton's second law. Now, some of you more read students would say, no, I disagree with you, Mr. Askey. It's F equals ma. No, that's Newton never said that. Newton. Now I'm not saying we don't say that today, but this is how Newton said it, because Newton came at force from a momentum point of view. Remember, he's studying momentum and conservation of momentum. He said, well, then what do I need to do to this object to change its momentum over time? And that was apply an unbalanced force. This is actually summation of forces. Summation of forces. Okay. Because sometimes you'll have 2 or 3 forces acting on something, and that changes its momentum through time. Okay, so that finishes the front. So we now have Newton's second law. And then on the back, now we're supposed to take that and do number 6. Now I sent them to the board, so I'll send you guys to the board. And when I send you to the board, what I do is I pause it again, and you work it without recording. So now work it on your own. Work using 6, using the numbers using the equation. Force equals delta P over T. Using our newfound equation, solve this one. It says, how fast will a dynamic cart? Remember that change in momentum is mass. Remember, little p is mass times velocity. So that's mv final minus mv naught over time. All right, so I'm going to pause it, and then you work on this, and then we'll come back together. And let's look at this one. Well, it says how far? It says standing start. So we know that V naught is 0. That simplifies this a little bit. This part goes away. 0. So force equals mass, in this case, times final velocity divided by T. We're trying to solve for final velocity. So V final then equals force times time divided by mass. When I plug in my numbers, I plug in a force of 10 newtons and a time of 3.15 seconds and a mass of 6.3 kilograms, same mass we had. I get an answer. V final should equal about 5 meters a second. So that tells me if the duck walker could keep that, it's really hard to do, keep that spring stretched to the 10 Newton mark, they could, within 3 seconds, they'd be moving at 5 meters a second, which is a pretty fast run. That's why we don't go that long, because it's really hard to keep it up. All right, now for the final phase of today, we're going to, yeah.
So on number 6, when the mass V naught equals 0, what about the time at the bottom? When it
time doesn't care. I mean, time goes to both. It's the denominator, but you know, if you want to split, you could split it up this way, I guess. You could say that is the same thing as, hold on. You could say that's the same thing as this. And then that's also divided by T. And then that part of the equation still goes away. 0 divided by anything is 0. So you're still left with, you know, mv final over T, algebraically. Okay.
All right, thank you.
Yeah, so for our final, good question, for our final little setup here, we're going to find out what is the acceleration for each one of those forces. And so we go back, look at our data again, and it looks like we're going to need an orange equation. And so looking at the orange equations, which one should I use to find acceleration? I know my delta x. I know my initial velocity is 0. I know my time. So which orange equation do I want if I'm going to solve for acceleration?
The second.
Right. So I have delta x equals, normally we just point, but we're going to write it down here, plus 1/2 AT squared, a blast from back in October. And so this part, it says we all started, the duck walkers, no, they started from rest, that's 0. So we have delta x equals 1/2 AT squared, and then multiply both sides by 2, divide both sides by t squared, and I get my acceleration isolated. So it's 2 delta x over t squared. So we're using this equation here, 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 and here, plugging in, well, each time I'll plug in, my delta x didn't change. My delta x is 3 meters. So that's 6 meters on top. So you're just going to take your A equals 6 meters divided by your time squared. And we have our time. Our times are all right here. Okay. So you plug in your time, square it. All right. Let's take a few minutes and do that. I'll move this over. Yes. Okay, it's already grouped. So I can look at my numbers here. Paste it right there. Right. So once again, I'm going to hit pause while we're doing the calculations. Okay, so we're back from doing some calculations here. Give me a thumbs up on the screen if you are in agreement with our numbers. I don't want to go plotting the wrong numbers. We need some verification. IO agree. Okay, tons of thumbs up. Okay, we're good. All right, so these are the values we're going to plot. And here's where the bonus or the winning class will come in, but I'll do purple. The bad news about us is with them, I had 6 sets of data and then we plotted all the dots. Here we're going to have 1, but tell you the truth, I kind of put together the time. So in a way, this is a combination of their classes. So 0, 0, 0 force gives me 0 acceleration. That has to be a point on your graph. And then now plot these dots, like go up 2, go over 0.3. Okay, go up 4, go over 0.459, et cetera, et cetera. I'll do this, you do yours. Whoa, 10 went crazy. Well, they were a little high on their 10. I will give you that. Okay. Now we're almost done here, but now the question is, what is that relationship? And that's why we need more points. Let me show you example. Let me show you their work. Here's, hold on. Here we go. So here's first hours. First hours dots, if you can see those, they look like that, a little scattered. If I were to, okay, so a little heads up here. If I were to draw their best fit line, it should be linear. It does seem like it's all kind of going that way. If I have to go through 0, 0, if I were to draw their line, oh, before I draw that, I'm going to put a big black dot where I think the center is. And the computers do this, but I think it's important. We only had 4 groups in first hour. That's a small class. Most groups had 6. We only had 4. So looking at 2, I'd put the dot like right there, right in between them, pretty much. And then for 4, I'm going to skew it towards this one. Maybe it's pretty much right there. And then look, 6 looks really good right there. And then we go to the next one, puts us about in there, seems fair. And then they wanted to get that one. This one is before. Now the ones you emphasize are because these are the best runs. So you highlight these would be this. I'm gonna highlight this different color. Hold on. Would be this, and this. Those are your three most important dots that you want to honor. Then you take this, you take your ruler and you set it up and you go, okay, you want to do a best fit line, honoring that, weighting those three with the blue haze around them, trying to get as close to those as I can and not cheating here. I know what the answer is supposed to be, but I'm going to just go by the data. Let me first draw this and see if that looks good. So light leads, that seem okay? That seems like it's kind of hitting best fit line for the black dots. I ignore all the other dots. Once I get a black dots, I ignore the other dots. And that seems pretty good. So I think first hour is going to be very happy. I'm going to have to kill all this though, because I don't want them to blow their surprise. Let me kill everything I did. Whoa, come on, man. Die. There we go. Okay, that's back to what it was. So that's how you do it. Like for here's second hour's data. Now you look at second hour is a little ahead of the rest of the classes. You look at second hour and their data, forget that blue line, the black line is their class average. See how tight their dots are? I mean, at 2, it's almost right on top of each other. And I thought, man, that's what you call precision. And so precision is if I'm throwing darts at a dartboard. Okay, if I have darts at a dartboard and I throw all my darts and it goes here, 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 and here. I have 5 darts. Though that is precise. It's not accurate. It's precise, right? To be precise, to be accurate, you're throwing in here. You want to be precise and accurate, but second hour is definitely precise. They get the precise award. Now third hour then looks like this. Third hour is more like first hour, a bit of a scatter. So we'll have to look at their dots. And your dots are here. Yeah, your dots are here. So let's go ahead and do a best fit line for these dots. Am I recording? Yes. Okay, so best fit line. Take this. We got to go through 0, 0. We know that point is correct. I want to get to I'm not against ignoring. Remember we're almost done here. Remember the 3 most important dots are this one, let's see, this one, and this one. The 3 highlighted, and of course, 0, 0. So these are my 3 most important dots, plus 0, 0. So if I'm going to ignore them, it's going to be the 10 and the 2, not ignore, but kind of not give a lot of credence to. So I would probably, for us, I would probably go about there. You see that it doesn't ignore the 10, but it still sticks with those 3 blues. You could move it up a little bit. I'm going to move it up a little bit. I think I'm giving the 10 too much credence. So I'm going to move it up and try and honor what I know is my best data. And these numbers aren't made up. I mean, they came from the morning classes. Sorry. Try it again. If I could, stupid. There. All right, so that looks pretty good. So there's our data. And that is as far as we got today. So we're going to leave it there. It's getting close to 2 o'clock anyway. Okay. So we're getting to another formula, and then we can work this. Then tomorrow, we'll wrap this up tomorrow. The homework, if you want to keep up, is take-home test, right? Try and do 2 and 3 tonight, keep up. And then maybe 4 and 5 tomorrow night or whatever. That way we won't be so crammed in the last day trying to get all of them done. Yeah, so tomorrow we'll finish this up. We'll start 5, 10. And then by Monday or Tuesday, we'll be on 511. That'll be it. Okay, so let's cut it off, and you guys can go anytime. You want to stick around and ask a question? I'll stick around with you.
Mr. Ask, I have a question.
Mm-hmm.
So on the take-home test on number 1,
Yeah.
where it's like V naught squared, So let's say like the number was 12 meters per second. Would it be like 12 squared, then meters squared, then second squared? Because it's V naught squared.
Well, if it's a V naught and you got to square it, you would say 12 squared meter squared, so 144 meters squared over second squared. Yeah.
All right, thank you.
Square the unit and square the number. Yeah. Okay. All right, good. See you.